an exploration of what the effects are of different controller parameters. One of the most ubiquitous controller parameters, the thing that you think of in every possible controller design that is linear in nature, the one thing that is in common, it doesn't matter what the shape of the controller is, whatever we have, so there can be lots of different parameters here. Not all controllers are PI controllers, so the dynamic part of a controller will always be some kind of combination of transfer functions. Maybe it's even got dead time or whatever. But every controller has a gain. Every linear controller has a gain that you can kind of think of as being factorable in this way, where it doesn't matter whether this is a pure integrating controller. When you think about a pure integrating controller, there's always some gain associated with that pure integrating controller as well. So what I'm going to say now is completely generic for all kind of controllers. And what we observe in general is that larger magnitude of controller gain, when we move from a place, and specifically starting from very low gains, as we increase the gain, good things happen. Okay, so the general rule is larger, and here I'm going to try and indicate those absolute values clearly. Like, the larger the magnitude of the gain, the better we do in terms of control, as a very general rule. Now, there's tons of people saying, well, what about except if? Obviously, yes. But let's say 4 small gains, making the gain bigger will make your control better. And I think the easy way to think about this is if we just have our kind of minimal control loop. I think it should be clear to everybody that when the gain is near to 0, the system does not respond at all to set points or disturbance signals. So if this is just 0, we can imagine that, like, control performance, if we have some kind of graph and we plot that as a function of Kc, and we like goodness, we can imagine that the like very bad is over here, okay, at 0, right? And so in other words, when we have a 0 gain for the controller is literally doing nothing. The set point changes and nothing happens. A disturbance happens, it has whatever effect it has on the output, and the controller doesn't notice, right? Or let's say the controller doesn't respond. The controller is simply outputting its default output all the time. And we can all agree that's not an awesome controller, right? So when the gain is 0, the control performance is bad. And so there's kind of nowhere to go other than having it work slightly better if the gain increases. And so you can kind of imagine that as the gain gets bigger, control performance gets better. And this is now where the what if kind of scenario presents itself. We start asking ourselves some interesting questions. If we start with this chart, there are some obvious kind of just scenario choices that we can think. So like, is this true? Is it true that if I just have infinite gain, I just have infinite performance, right? What are the limits on the magnitude of the gain? This is now, and I want you to have this picture in your head when you think about what you've read in 10.4, because there are, the textbook assumes this is relatively obvious based on what we've seen so far in terms of the reading that we've done so far. As we saw, well, when we had really simple systems and we had proportional control, yes, the proportional control wasn't awesome, but the bigger we made the gain, the better the control became. And we saw that like in the limit of infinite gain, if we made the gain really, really high, we effectively got perfect control for low order systems. And so let's just say, for some reason, this is a completely non-linear scale, right? But let's say perfect control is right there at the top. And what does perfect control mean? Perfect control means that, and you'll see this is in the book. If you've done the reading, you will have seen this term being bandied about. Perfect control means that y is equal to YSP. Okay, that's perfect control. That's the definition of perfect control. When I change y, or when I change YSP, immediately the controller gets there. And what we've seen is that perfect control is actually achievable kind of in the limit, right, for GP is equal to some kind of permutation of a first order system, okay? So if we have a first order system and we just have proportional control, the bigger we make the gain, the better the performance becomes. And if we just have super huge gain, we get zero offset and we get infinitely fast response. We saw that when we analyzed first order systems, that's basically the idea. Okay? Now there are some practical limits, but that's the general idea. And then we see that as things get more complicated, basically as soon as things get any more complicated than a first order system with no dead time, things get more complicated in terms of achieving perfect control. Okay? So we could kind of, in the limit of large KC, achieve perfect control for first order systems under proportional control. What's the obvious limit there is there are practical limits to the size of the gain that we can actually implement. Okay? So there's a practical limit over here. Which boils down to that idea that we've spoken about before, that it's super hard to build infinitely large things. Right? So it's very hard to build a controller that actually has infinite gain instantaneously. So yes, there's a practical limit in terms of just building a thing that can like effectively be an infinitely large gain, even at all, if we build it from components. There's another practical limit. Okay, so KC must be below some kind of upper bound, just from a practical point of view, because we're building it with physical components, right? And then there's another practical bound which has to do with the limits on the controller output itself, or the manipulated variable, depending on how you think about it. Because even if I have an infinitely large gain, or even if I have a super huge gain, right, I can only open the valve up to 100%. And so I have a lower limit which from a practical point of view limits the gain that is actually implementable. And typically those are this way around. In other words, usually it's much easier to calculate a large gain than to move a manipulated variable as much as the gain wants you to move it. And so right on the far end here, perfect control lives, very far to the right. So perfect control lives very far to the right. But actually in practice, there's a practical limit on how large we can actually make the KC that we calculate from a static point of view. And then there's another practical limit which is even smaller than that, which limits the amount of movement that I have to actually implement that move. And so obviously, even for the simple systems, in practice, I cannot achieve perfect control. And so we need to be a little bit like, we need to relax our requirements. Okay, so we can't say, here's what we do. We simply design for perfect control. That's not possible. And so one kind of relaxation that we can do is to say, we can do like relaxation here, saying, like, what do we want? Perfect control. When do we want it? Eventually. Okay, so this is like the first relaxation. Okay, no offset. And let me explain why that's a relaxation of perfect control, because it looks like this if you express it mathematically. Right, so that's what zero offset control means. It's like perfect control over very large time spans. Eventually we'll get there. So we don't achieve perfect control in the transient, like immediately. When the set point changes immediately, we don't get perfect control. But if it stays around long enough, notably, in most cases, we only try to do this kind of persistent control. In other words, we're just trying to reject persistent disturbances and persistent set point changes, and track persistent set point changes, with the idea that if the set point is moving all the time, from a practical point of view, we will never catch up to it. Exactly, right? So we have this kind of relaxation, and we can ask, now how do we achieve perfect control? If we think about the math, or how do we achieve zero offset control if we think about the math that we've read about in terms of closed loop transfer functions? Remember that yesterday, or like the previous lecture, we spoke about this thing. We came across these closed loop transfer functions for the same block diagram, right? Where we basically said, well, there's these two transfer functions that relate the set point and the disturbance, these guys. When the disturbance changes, this is the set, let me just expand that diagram. So the diagram actually has like, to get those transfer functions, there's a transfer function in there. So that's what happens when the disturbance changes, and this is what happens when the set point changes. And so now we can, if hopefully you were like clued up enough in CPN to look at this, the way that I've posed this relaxation statement, and immediately say, ha, final value theorem. Everybody immediately went there, right? It's like, oh, of course. That is like a clear place where I will use this thing called the final value theorem. See, when you look at this, the kind of nice math version of this is the limit as t goes to infinity of y of t minus ysp of t, aka e of t, right, goes to 0, or is equal to 0. It's the same math, right? Like if we say those two things, those two limits are equal, then the difference between them, the limit of the difference must be equal to 0. And we know what E of t is from a transfer function point of view, because we know what these closed loop transfer functions are, right? So we know that y is that relationship with ysp. And this is the closed loop transfer functions, right? So let's just call this GCL, just as a shorthand. And so you can see that if y is equal to GCL times ysp, imagine that we don't have a disturbance. It's the limit is important here. Okay, so I'm trying to talk about the magnitudes. So I'm trying to set that thing equal to 0. To get that error to be equal to 0, GCL must be equal to 1. I mean, and actually you can see on this level we're like really saying we need GCL equal to 1 to get y to be equal to ysp, right? So that's another way of thinking about what perfect control needs. And I mean, if you think about it on the top level, that makes a lot of satisfying sense, because it means to get y equal to YSP, it just means that this whole big block that connects YSP to y must be 1. Okay, and so that's what like the best controlled system wants to be, is like the best closed loop transfer function for set point to y is 1, right? And we saw that we couldn't get that right all of the time, but maybe we can get there eventually. And we applied this limit, right? And the final value theorem, the link here that I'm going through, is that the final value theorem says that the limit as t goes to infinity of some function of s, as some function of time, is equal to the limit as s goes to 0 of that function's Laplace transform. That's the final value theorem. We used it a lot in CPN last year. It's in the data sheet. It's totes in the data sheet. You totally used this. Okay, so I even know that I have a video of this. I know that you don't think of this as the final value theorem because most of you have optimized in your brain to the most common application of that, which is this rule to calculate the gain of a transfer function by setting s equal to 0. Okay? That's a consequence of the final value theorem. Does everybody here remember this idea? That if you take a transfer function, how do you find the gain of a transfer function? You substitute s equals 0 into the transfer function. Why does that work? Or just like, am I suddenly speaking in tongues? Like I'm having a very weird experience. Does everybody remember this idea? This idea that if you want to know what the gain of a transfer function is, like a quick way of getting the gain is you just take the transfer function and you substitute s equals 0 into the transfer function. Okay, some say yes, some say no. I suspect that the ones saying no have relied much too strongly on rewriting the transfer functions into standard form. But it is totes in the book. I have a video where I explain what I'm going to explain now. Maybe I'll cut this piece out. But it's because of this idea. I'm just going to explain this. Okay, this should be super familiar from CPN. Okay, if I have a transfer function, g, and I subject that transfer function to a unit step input, the eventual value of the output from that function will be the gain of the transfer function. Okay, is everybody still hanging on? Everybody with me? Okay, so how would I calculate that value? Okay, I would say this thing has the Laplace transform 1 over s. Okay, this thing has the transfer function g over s. Okay, this thing, let's call this y of s, right, is what I'm trying to figure out. But I'm specifically trying to figure out this thing, the eventual value, right? And so I'm actually trying to figure out the limit of as t goes to infinity of y of t. That's the mathy version of saying eventual value of y after having done all of this stuff. Okay? And so y of s, remember, is straightforward. Y of s is 1 over s times g of s. Okay? And I'm going to write down, the final value theorem has an s in there. So that's the final value theorem that you find in your data sheet. Okay? Yes, it has the s there. So that's the final value theorem. The function that we're trying to find the final value of is y of s, which is 1 over s times g of s. What is the final value of 1 over s times g of s, it is, I multiply by an s, which means the s's cancel out, right? And I end up just finding the limit of g of s as s goes to 0 equals the gain of the transfer function. Okay, now a lot of you have forgotten the derivation, but remembered the application. Right, so many of you just know, like you don't even know exactly why, but there's this rule that just says you take g of s, you substitute s equals 0, and that's the gain of the transfer function. Okay, but it becomes more important. I'm bringing the final, I didn't actually expect to have to recap the final value theorem, but I'm bringing the final value theorem in because this is kind of what we're trying to do, right? We're trying to figure out under what conditions do we get this eventual good control where we end up having 0 offset, right? And when you state it in math form like this, I'm hoping that all of you just recognize, well, that's exactly the final value theorem. Like that is totes the final value theorem, just like written down there. That limit as t goes to infinity, I'm trying to figure out what makes that 0. I have this thing over here. I've got my YSP in this case is, let's call it 1 over s, right? Because I'm trying to figure out what that response is. And so I'm trying to make E equal to 0. Effectively, I therefore want, as s goes to 0, the limit of that transfer function to be the transfer function that relates E to be 0. And we saw that that transfer function was over here, this, sorry. We saw that that was 1 minus GCL, right? So over here we saw that the thing that determines the offset is GCL minus 1. If we want that thing to be 0 eventually, it means we can kind of reason that we want GCL to be 1 eventually. Okay? From the final value theorem, what that means is we want that thing, the gain of that thing, to be 1 eventually. Okay? So now let's just investigate what these transfer functions look like. Let's just look specifically at the set point 1. And we observe, how do we bring about, how do we get that gain? How do we get the gain of that transfer function to be 1? Anybody who's not in the front row. How do I get the gain of that transfer function to be 1? We notice the only way that we can do this is, remember, we can't change GP, right? We can't change the process. Well, theoretically we could. We could build a new plant and have the control be better there, but let's say we're stuck with the one we have. But we have access to the front page or the front dial of our controller. Notice that this is a fraction, right? We're trying to get that thing to be close to 1. How do I get fractions close to 1? I get them to be close to one another, right? The numerator and the denominator. But I've got this unfortunate guy over here that's a bit blocking us from getting something right. Easy solution. We just make GP huge, right? Or GC. The bigger we make GC, the more that term dominates the calculation. And so that kind of in a nutshell, if you just look at these closed loop transfer functions, this is what we're buying by doing math. We're buying the ability to not have to experiment with every possible version of a system and see, you know, does it work in this system? Does it work in this system? Wait, does it work in this system? I've got a new system. It's like blue now. Maybe it will work here. I'm not sure. The math tells us that because of that, the bigger the eventual gain of GC is, the smaller the offset will be. It also tells us that if GC has finite gain, or let's rather say the correct version of this, which is related to one of the quiz questions, is if GPGC has finite gain, there will be offset. That's the math that drives offset. The math says this transfer function, if this transfer function is not equal to 1, at least eventually, there will be offset. It becomes equal to 1 if GPGC has an eventual gain of infinity large. Okay? We already spoke about the practical limits of having a static gain that is infinitely large. The wonderful thing, though, is it's actually quite easy to build a device that has eventual infinite gain. It's called an integrator. And so and basically what that means is any controller, any combination of GC, GP, which has infinite eventual gain, will reduce the offset to 0. That's really the rule, right? And so what does that look like? It just means that in the time domain, something with a response that looks like this, where that goes to infinity, will be the kind of controller that we need to reduce the offset to 0. But it also means that if the integrator is in the system, we also get 0 error.